Good morning, calculus students. Like I said on Monday, we will have another test next week, which should be somewhat of a relief in that we won't be covering as much material, but of course that won't be the case in the future. So what we cover through today will most likely be fair game. I'll be a little bit more specific about that on the announcement. But again, I will also let you know about the lectures next week. If we have a free lecture day like we did for the first test, I'll just have to make that determination. Usually that will be the case. And I will give you the same basically window of time to complete the test. Remember that one of the big pluses of the virtual classroom is that you basically have a lot more flexibility with testing. And that is really one of the positive things about having the online class. I think as we make our transition back to the classroom, maybe for the next calendar year, I don't know, in the fall, the spring, we will probably still be online. We will see that we'll probably have more transition to online than we had in the past. So what I want to do today is to go ahead and complete the information on the trig integrals by using a reduction formula, and then segue into the trig substitution method. If you took Calculus 1 at San Jac, you may have talked about inverse hyperbolic functions, and they actually provide a way to do the types of techniques we're going to do today. But standard mathematics usually likes to work with the standard trigonometric functions. So the trig substitution we do today has become fairly standard in the literature, and you'll, I'm sure, have already seen it. If not, we'll see it in your engineering and physics classes. So let's go ahead and look at the reduction formula. Now, the trig integrals aren't as difficult as the integration by parts, basically because they utilize concepts which we have been working with forever. That is trigonometry. So let me, there we go, clean this up a little bit. I've got the, let's see, the balance a little bit. I don't want to flush everything out, so you all let me know how this looks. What I want to do is remind you of the reduction formula. We've done some integrals where we just beat it to death with the Pythagorean identities and then utilize the calculus for the trig function to set up basically a power rule problem. And there's nothing wrong with that. But say that you had this reduction formula, and I gave this to you last time, but I'll repeat it now. I want to use it as an alternative approach to doing powers of maybe sine, cosine, or whatever. They're reduction formulas for all 6 basic trig functions. And I'll give you a list of those, and then we'll say more about them when we finish out the chapter. So the reduction formula starts with the first term, negative cosine u times the n minus first power of sine u divided by n. Then we have the integral, which we get from the integration by parts, n minus 1 over n, and then the n minus second power. So this is why we call it the reduction formula. Just like power reducing, we reduce the power. And so what I told you yesterday, and I'll just kind of spice it up a little bit, let's use this. Now in your notes, you can just write reduction formula. And this is what you would find in a table of integrals. So I kind of basically teach the integral table before we actually get to that section, because that's part of what you've been doing from the very beginning. So now, if we look at this particular example, let's try this one. Adjust this just a little bit. Say we have the 6th power of sine with an argument 3x. Now, of course, the way I taught you to do the fourth power was to use the power reducing formulas and then multiply everything out uh, and work it that way, just reducing to powers, single powers of cosine. And that was fine. But now when we get to the sixth power, we're thinking about cubing a binomial, which provides more algebra. So this is where you can say, if you're in an engineering class or physics class, or even in Professor Ron's Cal 2 class, you can use the reduction formula. And again, you just apply this until you're done. Now, when we use the reduction formula, we want to make this table ready. So this formula is from the integral table, and we have a 3x here. So first, we need to make it table ready. So we're going to have 1/3, because the u will be 3x here. So we have 1/3 sine to the sixth power 3x. Then I'll just put a little dot there so you can see it, dot 3 dx. Because here, and I'll put this right up above here, we have a u, which is 3x, and du, which is 3 dx. So when we want to use our formulas that we've derived, and this one by integration by parts, which is easy to do, you can look in the lecture notes. These are actually kind of fun to do. We dress it up as this. And so we've got the sine of u to the sixth power, and then we have the du here, which we'll just move along in the calculation. Now, the only thing that we have to remember, and this is important, is that we have this copy of 1/3, which we must just always have to the outside. So now we're thinking this isn't half bad. Say you need this in an engineering class. So we have our 1/3, and it's nice to use a bracket so you can see everything. And then we apply the formula. So we apply the formula to this to get this term and this term. So now notice we have n equal to 6. So we go up to the formula and we write the additive inverse cosine of 3x sine n minus 1, that would be 5, 3x divided by 6. Again, we keep track of the n for the reduction formula. And so there's the first term right there. It's going to have an 18 downstairs and a negative. That term's done. So this will generate the terms step by step. And then we move over to this part of the reduction formula. Again, n minus 1 is 5. So this is once we recognize the pattern, we just fill in the numbers. And that's the beauty of the integral table. But you have to respect the u and the du. So now we have 5/6. Now n minus 2 will be 4. So we have sine raised to the fourth power of 3x 3 dx. That's always our u. And then we close that off. So one pass of the reduction formula gives us this. Now, here's what's very important. We always have this 1/3 outside because that's part of our table ready procedure. And so now we see that we've run through this one pass and we have all the numbers that we need. And now for the next pass, we go ahead and distribute the 1/3. And then of course, now we will apply the reduction formula to this. So let me just kind of write above here, apply formula. And now we're going to have n equal to 4. So we have the 1/3 and the 6. So that's going to be a negative cosine. This is really, really powerful stuff. And it's really an improvement over beating yourself up with reduction formulas with trigonometry. So we get the 18. So this term is done. We don't have to worry about it anymore. We're just going to drag it along like we're court reporters. And now here, notice, we have the 1/3 times the 5/6. So that's going to be a plus 5/18. Again, the distribution is imperative. no distribution, and then we drown. So now notice we do the bracket again. So this part we apply the formula. So we have the 5/18 is now outside the bracket. So we go up to the formula where n is equal to 4, and we have negative cosine 3x, and now 4 minus 1 is 3. So we have the third power of sine of 3x divided by n, which is 4. I guess, we could teach, we could teach a really smart general math student to do this, but that might be a stretch. So now plus, now we go over to this part of the formula, and now we have n equal to 4, so we get 3 divided by 4. And now for the integrand, again, we have 4 minus 2, which is 2. So we have sine. We have an easy integral, which we could do without the reduction, but we're going to do reduction anyway because we're lazy. Why not? Just go ahead and use the power of the reduction formula. Always respecting the differentials. So now we're thinking, okay, let's go ahead and distribute. So we'll apply it one more time and we'll be done. So cosine 3x, sine 5 3x, fifth power. In the summertime, when we would do face-to-face, I'd say, well, do you want to do reduction or power reducing? And the students started to like the reduction formulas. I can't say that I blamed them, but then they hated to have to remember them. But you all don't have that problem. You have your notes and everything. So now we've got the 72 and the negative 5. So we have cosine 3x sine cube 3x. So that's that term. So these are done. These are fixed. And now as we move over here, and notice we have a little bit of reduction here. The 3 will divide the 18 and just give us a 6. So this will be plus 5, and then of course 6 times 4 is 24. So that reduced a little bit. I mean, you don't have to do it. You don't have to reduce it. It's not really going to matter. And so now, as we've taken care of this term, and the very last term, let's just see the reduction formula at work. Now notice we have n equal 2. So we run up here and we say negative cosine 3x, 2 minus 1 is 1, sine 3x divided by 2. And of course, that could be like the double angle formula for sine, but I don't care about that. We don't have to write it that way. And then divide by 2, as we have here, and then plus 1 over 2. And then, of course, sine to the 0 is just 1. And then we're left with our differential, which is 3 dx. That's the only time that 3 is going to matter. So you're thinking, wow, look what we did here. We applied the reduction formula to something that we usually use just the basic trigonometric reduction formula to do. So this is how powerful this formula is. And so now let's just write everything down and we'll be done. And of course, we'll tack on the arbitrary constant, because Webasine likes the arbitrary constant with the uppercase C. So we have our first term, negative cosine 3x sine to the 5th 3x divided by 18 minus 572 cosine 3x sine cubed of 3x. And now here, of course, we'll just have the 48 and the 5 with the negative. And of course, you can write this as the double angle. This would be half of sine 6x, right? If you doubled it, it's okay if you don't. And then lastly, of course, if we multiply this out, we got, this is just integral is just going to be 3x. So we get a 3 times a 5, which is, well, let's see, what do we have? 3, and then we've got a, let's see, I don't know if I dropped anything somewhere. I think I've got all the numbers I need. Yeah, that looks good. Yeah, because that's just going to give us a 3. Let me make sure I've got, I've got the 3 here, which I didn't run through, I don't think. Let me just check here. 5, and we reduce that. Oh, here we go. And then now, let's see. Let me just make sure we've got all this right. So we've got the 5 here, and then we had this reduced. And so we have now the 5 and this, the 48, and then we have the 5. Let me just make sure I did all of this correctly. I think I dropped something somewhere. I'll find it. So 5 here, we've got that. And let's see, this looks good. And then we have the 5 over 18. This reduced, gave us this. That looks good. Oh, okay. And now we're good to go because I reduced this. So that looks good. And so now this gives us 5 over a 48 here times the 3. So that will be plus 15 over 48 x plus a constant. And I think I've got all of my numbers in good shape. Yes, because see here, notice it, and sometimes it's probably better to just not reduce things, but I reduced it anyway. I just noticed this when I was doing it. When we multiply here, we reduce this, and then when we apply the reduction formula one more time, we get a 2 here and a 1/2 here. So we get the 3 times the 5, and then the x here, and then plus the arbitrary constant. So this will be a correct rendering of this particular formula. Now, let me just make a couple of comments here. When you use the reduction formula, of course, if this were just a plain old x, we wouldn't have to worry about the differential. But I put in a 3x just to make sure that we can respect the differential. So the first thing we do is we make it table ready. Table ready. And then what we do is we apply over and over. Once we have table ready, we have to remember the 1/3. And notice I multiplied the 1/3 throughout here to make sure that we've distributed correctly. So we have the 1/3, apply the reduction formula to this to get these two terms, distribute, and then apply the reduction formula again. Then we distribute, these two terms are fixed. And then here, of course, this gives us the 5 over the 24 when we multiply through. And note, we apply the reduction formula one more time here to get the -3 cosine 3x sine 3x over 2 plus 1/2, and then of course sine to the 0, which is 1, and the du is 3 dx. So that's the only time this 3 makes any impact on us. And so when we multiply this out, again, this is just 3/2 x. So 3/2 x times 5 over 24 will give us the 15 over 48x. And then of course the 5 and the -1/2, the 5 over 24 times the -1/2 gives us -5 over 48. So the idea here is that even though this may seem a little bit new at this point, it is still easier than application of the reduction formula. For the fourth power that we did last lecture, that was fairly straightforward. And that did not cause a problem because the algebra was fairly simple. But I think what is nice about this particular reduction formula is that it's clean and it's easy to apply as long as you make sure you respect the coefficients. And that's probably the hardest thing to do. I'm not saying that any of these techniques are simple, but certainly when the powers get larger, and you start raising binomials to larger and larger powers, you get an excessive amount of algebra. This just turns out to be a lot of arithmetic. We don't even do any integrals here. They're done automatically for us, and that's the only integral that we have to do, which is trivial. So again, use this and practice this. And let me also share with you some other formulas. You don't have to write these down. I just tabulated these. This was the formula that we just used. And this is what I wrote down when I taught my honors calculus. And they actually had to know how to prove every one of these. They didn't like that, but yeah, that's what you do in an honors class. You have to work 10 times harder. And then they had to know the formula proofs for Wallace. So that made it kind of difficult for them. So notice we have reduction formulas for sine and cosine, which I've stated, but we also have reduction formulas for the other 4 trigonometric functions. And so again, you can feel free to use these, but I don't want you to feel like you have to. As long as you have relatively low powers, it's okay to use the techniques with the inverse, not the inverse, but the Pythagorean identities. But again, this just shows you that using integration by parts, you can generate the so-called reduction formula. Notice each time the power of the integral gets smaller. And that's why they're deemed reduction formulas. And I always reminded my students, when you have negatives built in, they're easy to forget. So when we do this sine to the 6th power, we have that negative built in. So again, if you want to go ahead and start looking in your ebook through the integral tables, you're going to see these formulas. And again, they're used widely. So when we compare what we just did, we're seeing that we use the first reduction formula to compute this integral. And so try this several different ways. I think you'll find it to be a very useful addition to the techniques. Now what I want to do is talk about a trig substitution that basically has to do with triangles. Now, using triangles is probably a little bit easier for all of us. Let me move this out of the way. And we're thinking that if we have Pythagorean radicals, what's the best way to deal with them? So I want to first summarize them and then do some examples from 8.4. So this is what we're going to call trig substitution. Lots of times students will think, oh, once I learn this, I've got to use it all the time. But clearly you have many different paths to take. Substitution. Oh, I have too many subs. There we go. Substitution. I guess that's really substitution. And this is just a technique that deals with Pythagorean radicals, right triangles. And then, of course, when we don't have these, we have to work with horrible numbers and elliptic integrals. So this is a positive thing. So what I want to do is go through all the cases here, and then we'll do some examples. So case 1, we'll have, again, we're going to take a to be a positive number, and we're going to consider the radical a squared minus u squared. Now, again, this is a Pythagorean radical. We think of this with a right triangle. So what the trig substitution does is it utilizes a well-known trig function that can make this simpler. That is, what we want to do is get rid of the radical. Let me move Professor Ron over a little bit. What we want to do is get rid of the radical. So the substitution here is the following. That is, u, again, the a squared minus u squared reminds us of the inverse sine form. So we don't always have to use this if we already know another method. So don't pull this out unless you need it. So we have a sine theta. This is the standard substitution. So what students normally do is they put these on note cards and say, okay, well, this is a form that I recognize, and I can remove the radical if I use this. Now, first, let me just go ahead and take the differential. So if we're trying to set up an integral, we're going to need a differential. So du will be a cosine theta d theta. And we're using theta just for lack of a better variable, since we use the thetas with the inverse trig functions. So now notice here, if you like, this kind of gives us a way to write the inverse sine function, but I'll hold off on that and then say a little bit more about it. Or actually, let me just go ahead and write it. So equivalently, if you divide by a, u by a, and take the inverse sine, theta will equal the inverse sine of u over a. So this is where the inverse trig functions come into context. And then, of course, we remember for this particular setup, the inverse sine, so theta would live between negative pi over 2 and pi over 2 as we defined when we took pre-cal. Inverse trig function theory is very complicated. You know, we teach you enough in pre-cal to get you through calculus, but you can spend weeks studying this stuff. I mean, there's such a beautiful theory here, and we have to respect the mathematics like we did with the reduction formula. Now, so this is basically the setup from pre-cal. And then, of course, if we look at this, for instance, now we could say, well, what is a squared minus u squared? This will just be a squared. And then we'll have what? A 1 minus a sine squared. So again, when we factor this, both of these will have an a squared, and we're left with the fundamental identity. And this will just be a squared times cosine squared. So now the radical can be replaced with the square root of this. So then we have the radical a squared minus u squared. And of course, in the problem, maybe u is x and a is 4 maybe, or a squared is 4, and then we're good to go. And so this would be the square root of this. So now a is positive, so we just get the absolute value of a, which is going to be a, and then we just get the absolute value of cosine theta. Again, the square root of the square is the absolute value, but of course here with our inverse trig functions, the cosine function is non-negative here. So again, we just get a cosine theta. So if we want to eradicate the radical, we can use this substitution and then end up basically with a trig integral. So the first setup here is, if you notice, a radical a squared minus u squared, and it's not just the standard inverse sine form, then you can utilize this. Now, of course, there are going to be some special integral formulas that we're going to use, because we don't want to have to knock ourselves out every time. Like, we don't want to rederive the quadratic formula every time we use it. So this will be a substitution. That is, now, when we see this, we make this substitution. We have this differential, which we always have to write down. And then, of course, you don't have to memorize this. You can just kind of sketch out this part and go directly to here. And then the replacement for the radical will be this trigonometric term here. So this would simplify the integral, relieve us of the radicals, and give us a trig integral, which we should know how to do. Okay? Now, that's the first step. The other one, there are two more. We can have a is positive, and we could have the situation where these are flipped around. And now, if you like, let me just go ahead and draw the triangle with this. So we will often want to be able to write all of our terms with the given substitution. So now we can say, well, sine theta is just u over a. So we have opposite over hypotenuse. And then, of course, the Pythagorean theorem gives us the a squared minus u squared. So this would give us a triangle if we needed to interpret some things in our integram. So there's the concomitant triangle that comes with this substitution. So I'll go ahead and add that in. And most of you enjoy using the triangles, at least in this context, they're easier to work with. So now what about flipping this around? U squared minus a squared. So we're thinking, you know, we want to use Pythagorean, so maybe we could try the secant because we know the secant squared minus the 1 is the tangent squared. So yeah, that might be a good way to go. So now we'll say u equals a times secant. Again, these are not unique. You can make up any substitution you like. I mean, you could use cosecant, but these are just standard. And so the standard ones we want to do because if we communicate with our mathematical friends, they'll be using these too. So du will be a secant theta and then tangent theta, d theta. So just like we have here, we've got the u and the differential, which we'll always need in our problem. And then, of course, we can do the same thing, divide by a and take inverse secant. So theta is the inverse secant of u over a. Now, of course, this one's a little bit more complicated. Theta lives in the interval from 0 to pi over 2. Of course, we exclude pi over 2. That's an undefined. When you think about the way that we define the inverse secant, we do this so that the inverse secant always has a positive derivative. That's why the derivative formula has an absolute value in it. It's an increasing function. So we deal with the absolute value and just are happy that we have it. Now we can say, okay, well, u squared minus a squared will now be a squared times secant squared minus 1. But that's our friend, the Pythagorean identity. We've gotten really good at this, and we'll use this in the problems. This will just be a squared tangent squared. We find that to be really useful when we're doing the trig integrals, as we've already seen, and like I said before, we'll do it again. So now the radical can be replaced with the square root of this. So this will be the absolute value of a times the absolute value of tangent. Now, of course, the tangent, this is where, when we're doing integrals, we'll usually opt for theta here for clarity. Of course, if we run over here, then we've got sign issues that we have to deal with because we're in the second quadrant. So normally, we want to just think about our antiderivative living here. And if we do a definite integral, we need to make sure that these limits satisfy this particular part of the domain. But again, we don't always get everything as nice as this one, so we have to pay a little bit here. So of course, this will be a tangent theta. You'll see this in the lecture notes when theta lives here because the tangent is positive or non-negative. And then of course we have the additive inverse, which we might need to use if we're doing a definite integral when theta lives here. So the idea with this is that we will opt, when we do our problems with our indefinite integrals, we will opt for this. And if we do a definite integral, we'll need to make sure if we opted for this, that this was really where the limits live. Because then if that were the case, we'd have to choose this one. But again, we get the same equivalent antiderivative. We just have to work harder to get it. So unfortunately, not everything is as neat as this one, but we live with it. Now and of course, let's do the triangle. So now we have secant theta is u over a. So that would be hypotenuse over adjacent. So we have u over a And then, of course, u squared minus a squared. And of course, whatever u and a are, we fill those in. Now, the very last one looks like this. What if we had the sum? So we have a is positive, and we have the sum of u squared and a squared. And of course, we'll have some more integral formulas that you can put on your note cards to use. So in this case, we think, okay, well, with the plus here, it would be best to use the tangent function. So we have u will be a tangent theta. And this one's really well behaved like this one. We don't get the problems like we have with this one. And so now du will be a secant squared theta d theta. So that would be the replacement in the differential. And then now, of course, theta, if we divide by a and take the inverse tangent, we have inverse tangent of u over a. And then, of course, for the inverse tangent, we have those nice horizontal asymptotes. Theta lives between negative pi over 2 and pi over 2. Now we can go ahead and eradicate the radical, so to speak. U squared plus a squared will now be a squared times tangent squared plus 1. But tangent squared plus 1 is secant squared. That's the Pythagorean identity. So when you think about all of these problems and you think about what we're doing, it's interesting to note that all of this makes perfect sense. And it's like, wow, somebody was really clever to think about all of this. And so now when we take the square root, we have u squared plus a squared will now be the absolute value of a times the absolute value of the secant. But of course, in this range, the secant function is non-negative, just like the cosine. So we're in a good shape. So this is a secant theta. And so now the triangle here is just the tangent. So we have tangent theta is u over a, so opposite over adjacent. And then, of course, we get the square root here. So the beauty of the integration is that this just offers us a way to make an integral that we don't already know how to do. For instance, if it's a form that we already know from the inverse trig formulas that we learned at the beginning of the class, we don't have to do this. That'd be a waste of time. But maybe there's extra stuff that doesn't allow us to use those particular formulas. Now, I've got some additional formulas here that I'm going to share with you. They're called special integration formulas. But what I want to do now is just do some examples that utilize these new formulas. So let's look at them. And as we need them, I'll go ahead and reference our little cheat sheet. You don't have to reinvent the wheel with these, but you want to be able to write down enough stuff so you feel confident with what you're doing. So the first example will be here. This will be the integral, the square root of x squared minus 16 divided by x dx. Now, when we look at this and we think about this, we go back to this one. That is the secant substitution, because we have the x squared minus the 16. So we're going to use this substitution. So now, of course, we've got an x. So we say, in this case, x equals, notice we have a squared. So we're going to say 4 secant theta. Now, of course, if you make a substitution and it doesn't quite pan out, then just check your work and go back to your chart and make sure you got one that will work. So now dx will equal 4 secant theta tangent theta. Just take the derivative or the differential. Yeah, say those two words at the same time and you get what I said, which makes no sense. So we have the differential. And now, if you will, x squared, let's just go ahead and write this down, minus 16 will now be 16 times secant squared theta minus 1. So this is secant times tangent squared. So you can go ahead and write this down, or you can jump right to the punchline and avoid this. I'm just doing this now so it parallels what I did before. So now, if we think about this, the square root will just be now 4 times the absolute value of tangent theta. And so what we're going to do, we're just going to take the tangent, the theta in the first section of the domain for simplicity, because we just need an indefinite integral. We'll get the same with the other, but we have to work harder. So we're just going to say that theta lives here. Right there, just like what we had here. This one right there, okay? So now we have everything that we need. That is, we've got the differential. Just go ahead and put a box around everything that we're going to need. We might have to take some powers, but we've got the differential dx. We have the x, which is downstairs, and then we have the radical, which is right here. So let's fill everything in. So this is like miscellaneous substitution. You completely transform the integral. So we have the radical, which is 4 tangent theta, and the x is 4 secant theta, and then the dx is 4 secant theta tangent theta d theta. So when we look at this, we're thinking, well, this is easy. This isn't the 6th power of sine of 3x, so we don't have to use the big guns with the reduction formulas. So notice the 4 secants absorb, and we just get a 4 times tangent squared. So now when we look at this, we're thinking, okay, this is just the Pythagorean identity. So let's go ahead and rewrite it. So we're going to get a 4. So this will be secant squared theta minus 1. So we use the Pythagorean identity, so we have simple integrals. So now this integral, the integral of secant squared, is just tangent, so 4 tangent theta. And then, of course, the integral of just the minus 1 d theta is minus theta, so we get minus 4 theta plus a constant. Now, when you look at this, you're thinking, well, okay, well, we got a trig integral here that was really pretty simple. Not a whole lot of work to do. Sometimes you may have to do a little bit more work here, but it's okay. It's certainly easier than dealing with these radicals. So this is a really useful technique. It's like integration by parts. And so now you're thinking, well, the variable doesn't really mesh with the beginning. So this is where you can use your triangle if you want. You can use Pythagorean, but I know that takes a little bit more time. So now we can say, well, we've got secant theta is x over 4, so hypotenuse over adjacent. So that gives us an x squared minus 16 here. So now we can just fill in tangent theta is opposite over adjacent. So this is 4 times x squared minus 16 divided by 4 minus 4. And then, of course, now we've got the inverse secant, or theta is just the inverse secant of x over 4 like we did before. So this is 4 times inverse secant of x over 4 plus a constant. So now if you like, these 4's absorb. So we just get the square root of x squared minus 16 minus 4 inverse secant of x over 4 plus a constant. So this is like integration by parts. You kind of set it up and work it through, and how much time you spend on this is going to be dependent on how much you want to write. If you get very familiar with the substitutions, then you can write less here. But this is kind of like a minimal bit. You know, you just put down to make sure everything works out, and then you replace, create the trig integral, integrate, and then you can use the Pythagorean relationship here between theta and x to write everything in the original variable. So it is a powerful technique, but like other techniques, a little bit winded. Now, the thing is, of course, we don't have a form that fits this, and so this makes sense that we would use the trig substitution here. The idea, ladies and gentlemen, is that at this point, when you deal with lots of integrals that you'll see in engineering and physics, you'll either see a pattern that you recognize from the integral table, or you'll just try one of these setups and work it through. And of course, if you're really looking to save time, just have a nice, good integral table and find the pattern you need and fill it in. Nothing wrong with that either. Now, let's look at another example. Once we do this one, then I want to say a little bit. I've got some examples here where we do some special integral formulas. So here's another example with the trig substitution. And this is from your WebAssign. So we have the integral of 8x squared. And notice we don't have a radical here, but we still have the Pythagorean expression. We have 64 plus x squared squared. So we have a radicand that's Pythagorean. So we still can use the same technique. Notice we've got this set up. We have the u squared plus the a squared. Okay, so that's what we're going to use. Now, this one, again, not much different from the last one, but the absence of the radical can make you feel like, oh, I'm not really sure what to do with this, Professor Ron, but let me show you. It's very simple. We just follow what the symbols tell us. So now, again, we're going to let x be 8, in this case, tangent theta. Because we've got the plus here, we've got the a is 8, right? And so now dx will be 8 secant squared theta d theta. Good old Leibniz with his differentials certainly has made our life easier. And so now let's go ahead and figure out what we have. So x squared plus 64 will be 64 times tangent squared theta plus a 1. But now, of course, the tangent squared plus 1 is secant squared, so we get 64 secant squared theta. Now, again, we need the square of this, so we're good. We can square this to get that. And then, of course, the 8x squared, we can go ahead and fill in. So one thing we might want to notice here that we can go ahead and do is draw the triangle. So we have tangent theta is 8 over x, so opposite over adjacent. And that'll just give us the x squared plus 64. You can do it in either order. Sometimes you like to write it 64 plus x squared. It doesn't matter. So now we can fill everything in. So we have 8, but now we need x squared, so we square this out. So this will be times 64 tangent squared. So just square the x And now we need to square x squared plus 64. So we square this and we square this. So we get 64, I'll just write it out, 64 times 64 secant to the fourth. So again, we just get all these multiples here. It seems kind of ridiculous, but again, we need the square of this. So we square the 64 and we square the secant squared to get that term. And then we multiply by the dx. So this is miscellaneous substitution, ladies and gentlemen, like you did in Cal 1. So then we get 8 secant squared. It's like we go forward to go backwards. But now we got the 64 times the 64 upstairs and the 64 times the 64 downstairs. They're gone. They absorb. And now notice the secant squared absorbs 2 of the secant squareds here. So we get tangent squared theta over secant squared. Maybe I should have started with this instead of that reduction formula. This is a lot easier, as you can see. The trig sub is a favorite of calculus students because it's easy to do and you get to use the triangles. So now we're thinking, all right, well, now we're back to square one. We'll just use our Pythagorean identity that we use all the time on the tangent. So that's secant squared theta minus 1 divided by secant squared. So we can easily divide by secant squared. So secant squared over secant squared is 1. And then, of course, 1 over secant squared is cosine squared. So if we go, I mean, you might say, well, can I just write everything in terms of sine and cosine? Sure, but this is something we use quite often, and it makes for a simple 1 minus 1 over secant squared. So that's just 1 minus cosine squared. But of course, that's just sine squared. So either way you do it, you'll get the same answer. But this algebra is certainly a lot easier than converting everything to sine and cosine. Just let the identities tell you what the answer is without having to do too much work. Now, of course, when we get to this point, we don't have to use the reduction formula here that we did for sine to the 6. We'll go ahead and use the power reducing identity. So again, this will be the integral. If you like, you can do the 1/2 1 minus cosine 2 theta. So again, our reduction formula, sine squared, our friend sine squared theta will just be 1 minus cosine 2 theta over 2. So I just have the 1/2 times 1 minus cosine 2 theta d theta. So this will give us 1/2 theta. And then, of course, the integral of the cosine is the positive sign, but we need the 1/2 from the differential. So this will be minus 1/2 times 1/2 sine 2 theta plus a constant. So this gives us, so these are easy integrals, 1/2 theta minus 1/4 sine 2 theta plus a constant. Now, as you look here, you see that we want to use the triangle. So like in the reduction formula, I didn't bother to combine things. I want to write things in the form that we have for this one. And so now what we can see is we can use the double angle formula here. So let me just go ahead and write this in. This is something you know very well from trig. This is just 2 sine theta cosine theta. So we can get the single arguments instead of the double arguments. And so, of course, these twos absorb. So we get minus 1/2 sine theta cosine theta plus a constant. Oh man, Professor Ron, let me just let me write the whole thing over. I'm thinking, well, I just wrote the other terms. So 1/2 theta minus 1/2 sine theta cosine theta plus a constant. So now when you finish this off, all we have to do is basically, we can factor the 1/2 if you like, is go to the triangle. So now we can factor the 1/2. And then of course, theta is just the inverse tangent of x over 8. That's the easy part. Just using the inverse trig function. And then lastly, we want to just go ahead and replace sine theta and cosine theta with the triangle. So now we've got minus, the 1/2 has been factored. So the sine theta, in this case, will be opposite over hypotenuse. So we get x divided by the radical. And then, of course, the cosine will be the adjacent over the radical. And these are well defined, plus a c. So this will give us 1/2 inverse tangent x over 8. Then the radical is just giving us the x squared plus 64. So we get minus 8x over x squared plus 64. And then our arbitrary constant. So again, when you look at these types of problems, you don't really look at this and say, oh, that's the antiderivative. As we get more elaborate with how we work on antiderivatives, it's less obvious that this is actually an antiderivative. So really what you have to do is go back and check your work and make sure that you got everything right. The main thing with the integrals is that there's no step that's unimportant. You know, we often are frustrated by the fact that we have typos or that we drop a sign or whatever, and that's the thing that we have to be careful of. We're all human, and so just as I always tell my students when we get to the integration, just make sure that you are checking your work and doing your best work. The idea is to provide mathematics that's supported. So don't think that this is less important than this. Obviously, if we want to make a mistake, we'd rather it be at the end of the problem and not at the beginning. So be vigilant throughout, but see now that we have a nice technique that allows us to convert what seems to be an unfortunate integral into a simple integral, and then we can work it through. Okay, now what I want to do, ladies and gentlemen, is give you a formula, one of the special formulas. That is, we can use trig substitution to actually generate some nice formulas. Now, this particular one, I had this in your lecture notes. You can use trig substitution to actually generate 3 very nice special integral formulas. And here's one of them. So we call this the special integral formulas. So I'll give you one of them. And you can use the trig substitution technique to derive them. So say that we had this integral. You're in a physics class and you need to integrate. It's not a definite integral. You're thinking, well, this is an even function. If I could use some geometry or something, I'd be fine. But then you're thinking, this looks more like a, you know, basically not circular, but more hyperbolic, which is much more difficult. So if you looked at this particular problem here, this could actually be derived, and I'll share this with you. This can actually be derived using the tangent substitution, like I've done here. And you get our famous secant cubed integral, which we actually computed last week. So these formulas can be derived using the trig substitution technique. So what I want to do is summarize this and show you how you can use it, just like we did the reduction formula. So when we apply the trig substitution, we get 1/2 u square root u squared plus a squared. I mean, in some cases, it doesn't make sense to start from scratch unless we have to. So you need to be savvy with these, but then you also need to be able to utilize the integration table. So if we applied the substitution, in this case, u equals a tangent theta, through trig substitution, we could derive this formula, as you'll see in my lecture notes. Now, with that, we can actually compute the following integral from your homework. So you're asked to compute this: 16x squared plus 49 dx. So just like the reduction formula from the very beginning of the lecture, we want to make this table ready and then apply the formula. So again, with the integral table, it's like, you know, when I do my conference hours, I always say, did I write the problem down wrong? Or did we make sure we got it correct or whatever? The integral formulas must be typed correctly so that you follow every nuance of this formula. Now, when you look at this, we see, let's make one step here. Let's just go ahead and write all these terms as squares. So we get 4x quantity squared plus 7 squared. So that's maybe translating things a little bit. So now we have u equals 4x. So this is killing two birds with one stone. So du is 4dx. And now, of course, a squared is 49. From our, you know, we didn't have to do the 7 squared so much, but we see a squared is 49. And when we look at our formula here, we've got a bunch of a squares hanging out. But now we need the differential here so we can apply the formula. So we don't have a 4dx, we just have dx. So we're going to have 1/4 16x squared plus 49. And then we'll have 4dx. So now this is table ready. So we look at this and say, this is table ready. So now we can take this and apply this formula. So now notice we've got the 1/4, which is hanging out. And then we replace this with all of this. So we got the 1/2. And so we have our u, we've got 4x square root u squared plus a squared, 16x squared plus 49 plus a squared, which is 49, natural log u 4x plus the radical 16x squared plus 49 close plus a constant. So now we can go ahead and distribute everything. Notice we got our bracket here, and then we just put our arbitrary constant out to the left. So now notice this 1/2 multiplies everything. So this 1/4 multiplies everything. So we get a 1/8 here. So this will give us 4/8 times 4x, and then this gives us 16x squared. Let's see, I've got the 1/4, and then I've got the 1/2. Oh, here, let me do this. Yeah, that'll work. That looks good. Plus, and now we have the 1/2 times the 1/8, or 1/4, which is 1/8, times the 49. So this is 49 over 8, ln plus the 49. And now, let me check here. Notice that when we look at this, and I want to check something here. So we've got the 1/2, so we've got the 4 and the 4. Yeah, I've got too many 4s here. Sorry. That's what looked kind of weird. That's the 1, the 4's right there, and the 1/8 is right here. And so that gives us a 1/2. That looks a little bit better. So you can always look at your formulas here and make sure that things look right. So that gives us a 16x squared. Let me get my x squared in there. So here we've got the 1/8 times the 4. That gives us the 1/2, the x, the radical, and then the 1/8 times the 49, which gives us 49 over 8, natural log 4x plus the radical, 16x squared plus 49 plus a constant. Now, I will say this. This is quicker than going all the way from the beginning with the trig sub. We know I've taught you how to do the trig sub, but this is a standard formula. And so it's kind of like the quadratic formula. You can start over, or you can use the special integral formula to get practice using the table. The main thing is that we have the 1/4 here. So really, the 1/2 multiplies everything, and then the 1/4 multiplies everything. So here we've got the 1/8, which multiplies this to give us the 1/2, and here the 1/8 multiplies this to give us the 49 over 8. That's really the only difficulty about this. This is just like doing any reduction formula. And then the rest of this is just fill in the integral formula. So we don't do any integrals. We set up the problem to make it table ready, and then we fill in the actual expressions. So this is the beauty of the integral table, and you can see that just like learning problems in techniques in physics and engineering, we want to be able to use the tabulations to move our problems forward. And this is a very nice way of appreciating trig substitution. So now we're seeing that integration by parts and trig substitution give us some really nice integral formulas that can be very time-saving. Now, what I want to do is look at another special integral formula. So here's another one. So this has to do with the a squared minus u squared. So let's write this one down, special integral formula. And you can use these. I want you to use them. If they make sense to use them. Of course, I'll give you problems where you can't use them, but if I give you a problem where they apply, then you use them. So another integral formula looks like this, where we'll use the sign substitution. What if we have a squared minus u squared radical? So of course we could let u equal a sine theta. That was the very first one. Remember right here? That was the very first one. And so now you're thinking, okay, what does this formula look like? Well, here's what we do if we would do our integration or trig substitution. And you use the properties of the logarithms and all that. So I want you to look through the derivations in my lecture notes. But the main thing is, if you can't use it, then that's no good either. So I want you to be able to use these with some confidence. That's why I'm taking the time to go through them. So now when we look at this, we got that blasted 1/2 again. So we have the integral of the radical a squared minus u squared will now be 1/2, and we've got these two terms, u square root u squared plus a squared. Oh, sorry. Let me make sure. Oh, sorry, kids. X that. I wrote down the same formula looking at the wrong part of the page. Forgive me. X that. Too many papers. So here, this looks like this. This is much simpler. 1/2 a squared inverse sine u over a plus u square root a squared minus u squared. It looked kind of odd when I was putting a squared plus u squared. There we go. So this is the substitution u equal a sine theta. So now the derivation from your lecture notes is right here. This is the formula I just wrote down. This is the derivation, very simple. You get very simple integrals here, that like we've done before in our trig substitution, and then we use our triangle to go backwards, and we have a nice formula. So again, if we have a formula that fits this routine, we can substitute directly. And here's an example. So we have e to the x square root 1 minus e to the 2x dx. So now we can make this table ready because we're thinking this has this form. So this will be 1 minus e to the x quantity squared e to the x dx. So now when we look at this, we see that u equals e to the x. And in this case, the a squared, or the a, is just 1. So we have a squared equals 1, a equals 1. And this is table ready. Because now, of course, du is e to the x dx. So this is table ready. I want you to use trig substitution when you have to, but I don't want you to have to use a trig substitution on every integral when we have a nice integral table. And I do want you to, again, look through the lecture notes to go through that derivation just to give yourself extra practice. So now we can say, okay, let's fill in the formula. So now we use our integral table. So we have 1/2. A squared is 1. So we just get inverse sine of u over a. So that's e to the x over 1. So we have inverse sine of e to the x. And then we have plus u, which is e to the x, times the radical, 1 minus e to the 2x plus a constant. That's it. So I don't believe in busy work for busy work's sake. I would rather you understand this and use it when you know how, when you can use it. The idea, ladies and gentlemen, is that this is a very popular recurring integral that you see in physics and engineering. And so now we're looking at this and saying, wow, got my special integral formula, it's table ready, I'm good to go. Just remember, if you're going to use an integral formula, we have to make it table ready. We have to have the u and whatever parameters we need to move the problem forward. So again, you don't have to start from scratch on a lot of these. I don't want you to think that every problem is going to have a nice integral formula, but I do want you to use the integral formulas when they are applicable. So very good. Now what I want to do is do kind of an interesting formula that comes up in this class where we can't use our nice integral table, but we can still weather the storm, so to speak. So sometimes we get these interesting formulas. You know, you can use integration by parts to integrate inverse sine. But when it comes to inverse secant, let's look at this one. And then, of course, we're assuming that x is greater than 1/6, so that when we have our differential, that is the absolute value of x will be x in this case. So we don't have to worry about negative signs. This will actually make sense. And so now, when we look at this problem, we're thinking, well, the only course of action we have here is integration by parts. We can certainly differentiate this, and we can use this little gem here to avoid negative signs, the absolute value of 6x just being 6x because of this hypothesis. But we're thinking we don't want to integrate it because we don't know how to do that. So we can use parts. So start, use integration by parts. I guess if you really had the best integral table in the world, you'd never have to do any integral again. But that's sometimes difficult. But of course, computer algebra systems have made computing obsolete in a lot of cases, which is not good. You still need to be able to compute and know how to use the integral table and work the problems by hand. So now we have inverse secant of 6x. And then, of course, we just have plain old dx. This is like one pass, and I'll be formal here just so everybody feels good. This is not, you know, like repeating integral or integrate or differentiate to zero type thing. This is just one pass. So now when we do this, we have what? The differential is 6 dx. And then we'll have 6x, the absolute value of 6x times the square root of u squared minus d squared. So this will be 36x squared minus a 1. So that's the derivative of the inverse secant. And then, of course, the dx just gives us an x. And then, of course, the 6 is absorbed. So now we get the plus with the integration by parts formula, and then the minus. So now this implies we have secant, inverse secant of 6x dx equals, so we have x times the inverse secant of 6x. That term is fixed. And then we have minus, and now notice here, the x is absorbed here, and the 6 is absorbed, and this just leaves us 1 over this integral. So we don't have a special integral here. We don't have the radical upstairs, so we can't use a special integral formula, which you certainly could use, because I've told you about them. You certainly can use them and use them to good health, as they say. Now, since this is in the denominator, we want to use the secant substitution. So this will require trig sub. So above this integral, just write trig sub. And doing the trig sub makes you better at every integration technique we've done so far. It helps us review everything. So now, when we look at this, we can let the u, in this case, we can have 6x in this case. So let, I'll do a let here more formally. 6x equals secant theta, because we want to be able to square it. So, and of course the a is 1, a squared is 1, a is 1, so that's easy. So we just have 1 secant theta. So the u here is 6x, u equals secant theta. So that's a little trick there. Notice this is 6x quantity squared. So that's the u squared minus the a squared. So again, think of this as the u. So now we get 6 dx equals secant theta tangent theta d theta. Okay? And now, if you will, 36 x squared minus 1 equals 36. And in this case, we get secant squared theta minus 1, which is what we want. So we can get the tangent squared. So this is 36 tangent squared. So now the radical will now be 6, and we'll have the absolute value of tangent. But now, of course, we're back in the same situation. We're going to check this by allowing theta to make our antiderivative process easier to live here. So we have a positive tangent right there. So now we can make the substitution and be done. So now our integral will just say equals x. And if you like, and I guess this is important, let's just go ahead and draw the triangle. So we have, in this case, theta, or if we look at this, secant theta is just going to be 6x over 1. So we get hypotenuse over adjacent, so 6x over 1. Of course, the theta is right there. And this gives us 36x squared minus 1. So just basic trigonometry here. So now we get x times the inverse secant of 6x minus, let's fill everything in. So we get, now dx, we get 1/6 here. We got a 6 here. We don't need 6 dx, so we'll do 1/6 secant theta, tangent theta, d theta. And then downstairs, we need the square root, and that's going to be what, in this case, we're going to have what, 6 tangent theta. Interestingly, so here, the tangent theta, so let's see, do I have too many, oh, I do. I've got too many 6's running around, because 36x squared is just secant squared. There's no, I knew I'd have too much there. There's no 36 there. Sorry about that. That looked kind of weird. Notice 36x squared is just secant squared. There's no 6. Mine playing tricks on me. There you go. So that's just plain old tangent. So no 6 there. Scratch through that. The math always tells on you when you lie. So inverse secant 6x, and now we can factor the 1/6, and the tangents absorb, leaving us secant. So again, this one's a little bit tricky. Let me just kind of say more about this. Notice the 6x is the secant because the a is 1. And when I square this, I'm just squaring the secant. There's no 6 there. I threw in a 36, and that was making it up. So get rid of that. So now we just have the secant integral, which we know from Cal 1. So x secant inverse of 6x minus 1/6 natural log secant theta plus tangent theta plus a constant. So again, when we look at this problem, at first it's like, man, this is difficult, but it's not so bad. We start with integration by parts. This is more difficult. This is probably the most difficult trig sub we've done so far, because we have to start with integration by parts, and then we have a substitution, which is a little bit atypical. Our u is 6x, so, and our a is 1, so we have 6x equals secant theta. So that's a little bit different from before. We got that factor running around, and so when we square everything, we just get the secant squared minus 1 with no other factors. And so, of course, let me just go ahead and get rid of that one too. So everything looks good. And then, of course, we select this to make our integration process simpler. And so our triangle's easier. Otherwise, our triangle's more complicated because it would be now in the second quadrant. Now, what we can do is use our triangle to rewrite these terms. So we get x inverse secant 6x minus 1/6 natural log. So now secant, we already know what that is. It's just 6x. And then tangent is opposite over adjacent. So we just get the square root. So that's a very elegant problem and one I want you to master because there are all the pitfalls in this problem. That's what calculus is. Calculus is an art form. The beauty of the calculus, though, is it tells you how to work through the problem. And it tells you when there's an inconsistency, because a lot of times when you work things, you're thinking, well, okay, I see that factor from here, but wait a minute, why do I have an additional one here? And then I look at it and say, okay, well, it's a matter of interpretation. So again, we have to make sure that what we write here is not what we think, but what the symbols are telling us. So symbolic computation will always tell on us when we do something that's incorrect. So now, again, I want you to work through this problem. This is a nice WebAssign problem. I want you to master this technique. And then, of course, if you like, you can just change up the numbers. Change this to, 49x squared minus 9. And see how it changes the numbers. Just same technique, but just different numbers. Okay, now, again, just remember, as you work through the trig sub, you get to review everything we've done so far. All the techniques are here. Even when you do the integration formulas from the integral table, they help you review the idea of keeping track of constants. Because when we're working these integrals, we have constants running all over the place. Now, this example here, I like to stick with the secant. You're thinking Professor Ron likes that secant substitution. Well, the reason is because it can be a source of error. So let's look at a definite integral. So now we have the integral from 5 to 10. And in this case, I think Professor Ron might even change the limits, just to give you a good example here. So we have x squared minus 25 divided by x squared dx. Now, when you look at this, ladies and gentlemen, this doesn't, I mean, you could scour an integral table for long enough and probably find this form and fill it in. But I don't want, unless I've given you kind of a green light to use the integral formulas, like the special integral formulas that I'm giving you, I would want you to do this by the trig sub. But again, like I say, when we look at this, we're thinking, okay, this is going to be a secant substitution. We don't have the 36x squared, so we don't have to worry about that. Just remember, as you're working these, if you've got the 25x squared, then you've got the 5x equal whatever, just like we did on the previous problem. So now we're thinking, okay, this is going to be a situation where it would behoove us to change the limits, so we would make sure that we had the right portion with the absolute value when we're dealing with the secant substitution. So let's do that first. So notice that we'll have x equal 5 secant theta. So I know we keep going back to this. That's this one right here, which we just can't seem to get rid of. So now we have dx equals 5 secant theta tangent theta d theta. Nice problem. This is a good problem. And now we say x squared. Always do this computation just to verify what you're doing, just to make sure everything looks good. So we're going to get a 25 secant squared minus 1. So this is again, remember before the 6 was over here, so I didn't have a 36. That was overkill. If the 5 is here as it is, you have this. So that was the difference with the last problem. So don't fall into that pit. And so now when we look at this, we have the radical x squared minus 25. Go ahead and fill this in, 25 tangent squared. So this will be 5 absolute value of tangent. Now, notice here that this will prescribe which of these we need to choose here. So let's go ahead and look at where the thetas live with these limits of integration. So now we have what? 10, this right here, right? 10 equals 5 secant theta. So equivalently, 2 is equal to secant theta. So of course, with the inverse secant, we know that in this case, theta would be what? Pi over 3. Because that's in the range of the inverse secant. And then we have 5. Well, these are doable. These are on the unit circle, so at least we get nice numbers. If not, we just put the symbolic form and be happy with it. That's not a problem. So now we have, in this case, secant theta equals 1. And of course, that's the cosine, basically. So we have theta equals 0. So our limits actually lie in the portion where this is positive. So we will take theta here, 0 to pi over 2. My work is always steeped in how we work through things. It's not a matter of doing things like a computer. It's utilizing your ability to process the problem. And so when I tell you about something, I'm not just boring you with details. These are important details. This is the difference between becoming excellent at math and staying mediocre. I'm trying to give you processes which will make you better. And mathematics, just like any profession, is a continuing education. I mean, you think you know a lot now. I mean, when you go, if you eventually go to graduate school and get an advanced degree, you're going to think, well, how did I survive before I became an expert? So the idea is once you get your engineering job, you're going to learn every year. And by the time you retire, you're going to be a brilliant individual because you will have learned every year. So think about math that way as a continuing education. So now we see 0 to pi over 3 will mesh with this. So this will give us 5 tangent theta. So this works. This works for these limits. And so now, do we have everything we need? Well, we certainly do. So let's go ahead and fill it in. So this will be 0 to pi over 3. I never change limits. I always use the original, but now we kind of were forced to with this example. We needed to check this. So now the square root will just be what? 5 tangent theta. And then, of course, we got x squared, which will be 25 secant squared. Just square it out. And then we have the differential 5 secant tangent. At least the integrals that result are easy. The setup is what takes a little bit of time, but then the resulting integrals are often very easy, or ones you know. Like if you get the secant cubed integral, then use the formula that we derived. Don't rederive it. That takes too much time. So now notice we got a 25 and a 25. Those hit the road, and then we've got 2 copies of a tangent and 1 copy of secant that survives. So we got 0. We have 0 pi over 3 tangent squared theta and 1 of the secants that survives. It's weird when you do these problems there's a certain pattern that will always ensue. And when you write it, you'll have a sense of peace about it. It's like, okay, my numbers look good. Things look good here. And this is how we see this problem. So not always will you get this nice absorbing of coefficients, but it does happen often. Now, of course, we'll use the same old trick because we're lazy. We'll just write this as secant squared minus 1. That's why I did that problem for the last class, because I like to use this identity. You can always change the sines and cosines, but I like to think about ways that make the problems easier for my students. So we have 0 to pi over 3. So that'll give us a secant theta, secant squared over secant. And then, of course, 1 over secant is cosine. So we get minus cosine. So now we've got integrals that we know from Cal 1. It's amazing that when we do these problems, we simply apply a bunch of pre-calculus, calculus 1, we call it Cal 2. Ladies and gentlemen, calculus 2 is a topics course, okay? We use math, we learned some new techniques, but it's the math you learned in Cal 1 and pre-cal. So we're doing a topics course basically. And so now these are easy integrals. So we get the what? What's the integral of secant? Well, that's the Lagrange method, the natural log of secant theta plus tangent theta. That's a famous theorem which we've used many times so far. And the antiderivative of cosine is the positive sign, so we get minus sine. Zero to pi over 3. So now, when we finish this, all we need to do is the fundamental theorem of calculus. So we've got, let's see, just do a bracket. So we have ln of secant of pi over 3. These are all on the unit circle, plus tangent pi over 3, minus sine pi over 3. That's the first portion. And then minus, and we put in 0. Well, that's going to knock off everything pretty much. Secant of 0 plus tangent of 0 minus sine of 0. Well, of course, that's 0, but just write it out. You can compute in your head, but that usually leads you into a sinkhole because you assume something. We all do it. So just go ahead and write things out so you can go back and check. So now we have natural log. Okay, now secant of pi over 3, that's 2. Well, boom, right there. And then tangent of pi over 3 is just square root of 3. That's just square root of 3 over 2 divided by 1/2, which is square root of 3, and that's a positive number. And then, of course, sine of pi over 3 is root 3 over 2. And then, of course, over here, what do we have left? We have minus natural log. Well, secant of 0 is 1, and of course, tangent of 0 is 0, so that's just log of 1. And then we have minus plus sine of 0. Well, I won't write that out again. That's just 0. So plus 0. And clearly, the natural log of 1 is 0. So we just get natural log of 2 plus root 3 minus root 3 over 2. So again, when you think about doing the definite integrals, and this is why I did this, when I think Dr. Larson makes a mention of this in your ebook, that's why this textbook is so good. Dr. Larson, like I said before, is by trade a topologist and quite an excellent mathematician. I had the opportunity to meet him about, I guess it was like about 7 years ago. And he's very active, and his book is world renowned. But Ann Caven, who used to be the representative from Cengage, brought him to the campus and said, "Ron, you need to meet Dr. Larson." And his name is Ron, Professor Ron. I said, "Good, I feel like we're kindred spirits." But the thing is that when you look at the mathematics from a standpoint of procedure, you know that every step that you've done is correct. So this is a good example. Now, let's look at another one. The idea behind most of these problems is that when we work on trigonometric substitution, the idea is we want to be able to manifest what we already know and then produce a technique that's reproducible. Now, I've got an example here that I always do the inverse secant one, but I have one here that I want to look at. Let me find it. Let's see, we've done that one. Oh yeah, here's one. And what I want to do is look at a situation, this is from your WebAssign, finding the area enclosed by an ellipse. Now, this is where you might think that if we look at this, we might be interested in the special integral formula. But I want to show you a trick which I've done before. And Dr. Larson puts this in this section, I think, just to trip you up. So look at this one. So we have area enclosed by the ellipse. I worked a problem with a student yesterday where we had half of an ellipse and we had to find the actual center of mass. So that was a fun problem. Area enclosed by an ellipse. And we've got x squared over a squared plus y squared over b squared equals 1. And then, of course, if we solve for the positive square root, we get y is equal to b over a square root of a squared minus x squared. So this is the principal square root. So what we want to do is just draw the standard ellipse to get a picture of this, to make this kind of like a problem we would have done in the first section of chapter 7. So let's just go ahead and draw our ellipse. So we have y-intercepts and x-intercepts. So now when you look at this and you think about this, let's just go ahead and first set x to live here between negative a and a, not even using any so-called symmetry right now. We're not so much interested in that. So we might take an x here and then just look at the rectangle. So now we have the upper curve, which is this one here, y equals b over a square root a squared minus x squared. And then we have the lower curve, the additive inverse. So now, if we think about this point here, we have x, we've got the upper curve minus the lower curve. So we can get the length here, in this case, length equals 2 times b over a square root x squared minus a squared. Okay, so again, this is where we're not really trying to use any symmetry. We're just going to pan all the way across and basically have the square root minus the additive inverse, which gives us 2 copies. So this is how we can set up the area calculation. Okay, and again, we know where x lives. So this implies that the area enclosed by the ellipse is now, so we'll say the integral from negative a to a, upper curve minus lower curve. So we get 2 times b over a square root a squared minus x squared dx. Now, this is where we want to look at this and be careful about this, the way we've set this up. Now, notice as we pan across here that we get a very nice geometric setup, which we're going to see from this integrand here. So this gives us 2 b over a, the integral from negative a to a of what looks like a special integral, a squared minus x squared dx. Now, when we look at this and we think about this particular setup, notice in this particular case that we get the entire area of the ellipse by setting up this integral, okay? So this covers the entire ellipse. And now, when we look at this portion here, and if you like, we can go ahead and let me just kind of leave this so you can see that. Let me make it a little bit more obvious. And this is what I used in the problem that I worked yesterday. This is now just a semicircle here. So this problem right here, just like we used yesterday, is now just a semicircle. So this is a little bit different from the original problem. This looks like this. Now change the scale a little bit. And we've used this before, but I want to make sure that it's clear now. And so now you get that. So this integral right here is the area that we have here, which is half the area of the circle of radius a. So now, just like we've done before, so we get equals 2 times b over a. And so this will be half the area of the circle of radius a. So that's 1/2 pi a squared. So the boxes correspond. So this gives you 2a squared b times pi over 2a. The 2a's absorb here, leaving us with a pi ab. So what I think Dr. Larson was thinking is that, well, you're just going to use the special integral formula, but you don't have to. The idea here is that now when you look at this, it's like we're going to go back to the same techniques which we used before when all we could appeal to is the geometry. But if we actually used the special integral formula here, it would still work, but that would be overkill. But again, it just really depends on how you're thinking when you do the problem. But notice here, there are many ways to go about computing areas of geometric objects. But the interesting thing here is that I spent this time, for instance, if you remove this and it's a definite, indefinite integral, then you have the integral table. You have to use the integral table or start from scratch with in this case, x equal a sine theta and do it the trig substitution way, or use the integral table. So I wanted to, when I did the problem yesterday, I thought about this example that I had assigned in your web assignment. I thought, well, let me just go back to this and show the students that you can still appeal to the original technique. So when you're working a problem, ladies and gentlemen, it doesn't matter what mathematics you use. You can use what you've learned, or you can use a combination of what you learned and what you already know, or you can throw that all away and just say, okay, well, I learned how to do this in Calculus 1. So the beauty of the calculus here is that there is no set way to do anything. And you can often look at this and say, oh, well, let me try that special integral formula to see if it works. But notice if we were going to do that, this is a nice even function on a symmetric interval. And then we could hit it with another 2 and then go from 0 to a. So you can make all kinds of simplifications and do this problem in many different ways. Now, what I wanted to do is just to take a little bit of time to go through one of these derivations, because I keep saying you need to work through a derivation of one of these special integral formulas. So let me share that with you. I just want you to see that you can work through this. And then next class, what we'll do is we'll start partial fractions, which is going to remind you of pre-calculus. So that'll be fun. So the particular integral that I wanted to do was the one that I've spent the most time on because it's the worst. Let's start with this. And I want to go through this and go through the steps with it. Now, when we try to, all of this part right here has to do with what we've already talked about. For instance, when we're doing the trig substitution here, we made this substitution and we figured out what u had to be and what the angle would be, and it would live here. And then, of course, we have the choice of picking either one of these depending on where theta lives. And of course, if we were doing an indefinite integral, we'd always choose this because the triangles and the arithmetic would be a lot easier. So this we've already done. So what I wanted to share with you is the derivation of the actual special integral formula, which we've already used. Now, we did the tangent one. Let me just go back and share with you the ones we've done. We did the sine one right here. And then we did the u squared plus a squared one right here. Okay, now I want to share with you the other one, this one. So how do we do this? Well, we go ahead and fill in everything. That is, the u squared minus the a squared radical is just a tangent theta. So we're going to do our derivation for theta living here. Again, because it's easier to keep track of the arithmetic. And now, then we're going to say, what's du? Well, it's a secant theta, tangent theta, d theta. So like we have here, we have our differential right here. Oh, sorry, can't see it, right there. Okay? So now, when we multiply this out, we're going to get an a squared copy that we factor, and then we'll have the secant theta times the tangent squared. Okay, so now that's a trig integral, and you look at that and say, well, okay, the derivative of secant is not tangent squared. And then I'm thinking, what do we always do when we have tangent squared? We replace it with secant squared minus 1. That's our bread and butter. Okay, so when we do that, we're going to get secant cubed when we multiply and a secant integral, all hit with the a squared. Now, we did this one when I taught you integration by parts. So we don't do it again. We're not, we're clever people. We like what we do, but we don't want to knock ourselves out. So remember, you go back in your notes, we did this integral, the cube integral, using integration by parts. And then, of course, our friend here, the integral of secant theta is the natural log of secant theta plus tangent theta. So this part right here is the formula that Professor Ron derived using integration by parts. And remember that the integral repeated. And so we had the first instance of the algebraic solution for an integral problem. Okay, so you're thinking, all right, well, Professor Ron, we've integrated, we're done, right? Okay, well, what I want to do at this point is to neaten things up a little bit. Now, when you actually do that and you think about this, we want to think of, okay, how can we change this up a little bit? Now, I went ahead and factored the a squared and the 1/2, and then notice here, I've just called the constant a C1 right now because I don't want to give it any kind of special name. Now, when we get to this point, at this point in the derivation, we go to our triangle and we write the secant theta as u over a, and we write the tangent theta as the square root of u squared over a squared minus 1. And here I'm using the Pythagorean identities. So they look a little bit different instead of the triangle. And so now I do the same thing here. I write them in sum. And then you just get a common denominator here. Now here's the deal. The common denominator here is a, and then with the minus minus, we just throw this out here using the laws of logarithms. And then what's left behind is the natural log of u plus the radical here when we get the common denominator u squared minus a squared. And the same thing over here. Now, at this point, we just want to clean things up. Now, when I look at these and I think about, okay, so what do we do next? If we multiply through by the a squared, these absorb, we're left with the 1/2. And then this particular constant here will be absorbed into the C1. And then when we're done, we just call the new constant C because we're lazy, we like that. And then what's left is this particular formula. And then let me go ahead and close this off with the parentheses. So now what I want to focus on here with this particular derivation, again, it's not very difficult, is just to note that it's a straightforward application of the trig substitution. But when you look at it, you've got all these letters running around and you have to use the properties of the natural logarithm. And so once you compute this, you have this as a ready formula to use when you encounter it. So the idea here is that if you have an integral like this on your test, you are certainly welcome to use the special integral formulas. I may test you on that. I would like for you to be able, as we've done in class, to be able to use the integral table. And so we learn how to use the integral table before we even get to that section, because I focus on the Weierstrass substitution when I get to that section anyway. So the idea here is that we use the trigonometric substitution, and then we use properties, identities of the natural logarithm to actually affect the proof. Now, when you look at the other derivations, the first one here with the sign substitution is much easier. You don't have all the logarithms here. You just have very simple integrals. These are easy. This is a very simple derivation. The one with the secant substitution is much more complicated because the integrals are more complicated. And then this is a trick that mathematicians always use. You just kind of push aside all of the constant terms and shove them into one constant and call it C. So that's why these expressions here are so much more simplified. We want to whittle them down to the neatest possible formula like you do in a physics class, and then couch everything that's not very attractive in the formula into the constant, because they're arbitrary numbers. When you put arbitrary numbers together, you still have an arbitrary constant. So this is how you actually derive these formulas. We've done this so far, but this has probably been one of the more complicated setups that you have to do. So I want you to work back through this and know that the trig substitution, just like the integration by parts, can give us very, very nice integral formulas. And these are the formulas that make up the integral table. And integral tables, ladies and gentlemen, are voluminous. you would be amazed if you just look at the integral tables in this text, and you'll see these formulas, and you'll see other formulas that can also be generated using partial fractions. So the idea here is that we want to generate as many integral formulas as we can, giving you enough techniques to weather the storm. And then when you get to engineering classes, your engineering professors may even say, okay, well, I need you to learn how to work with these integrals. And they will be different techniques. A lot of times I tell my students to get the advanced calculus. I don't have it right here with me, but get the advanced calculus Schaum outline. It has elliptic integrals, and the gamma function has a lot of nice examples that will serve you very well as you move into some of your engineering classes. My students always come back and they ask me questions, and they say, tell your students to study that calculus, because when they get to engineering, the professors will demand that they know it. So like I say, most of my students have gone either to Texas A&M or the University of Houston main campus, and they all say the same thing. They all say the same thing. The math is the great divider. You survive the math or you don't survive. And it's the math that will keep students from finishing a degree in electrical engineering. So don't allow that to happen. Just understand that as you work through these problems, there's always a process, and there's always a process to make things neat. So what I'll do, I'll put up a announcement about the second test. I've gone ahead and posted the trig substitution section, so I want you to go ahead and start working on that. Go ahead and knock out your other integral problems, and again, we'll have the window of time for the second test, just like we had for the first test. And then I'll let you know about the extra lecture day. On Monday, I'll cover partial fractions. And of course, none of that will be covered on the test. And I'll let you know about the Wednesday if I want to have a short lecture or just give you a free day to rest and study up for the test. I appreciate your attendance today. Just remember, as you work through this section, it's going to make you better at the previous sections. So I appreciate your time today. I wish you well as you study, and I will send out invitations for office hours. If I see you there, fine, or otherwise I'll see you on your WebAssign messages, and have a good week of study. Bye, everyone.